important component of modern astronomical theory. Literally speaking, if dark matter did not exist, much of cosmology would simply collapse. The belief that the universe must have an additional invisible matter component was formed in the 1930s, when astronomer Fritz Zwicky was studying galaxies moving around each other. In the Coma cluster 320 million light-years from Earth, he discovered that the galaxies were moving so fast they would fly apart from the cluster, simply because gravity was not strong enough to hold them together. However, there are many such clusters throughout the universe and no galaxy appears to be flying away. So clearly something is holding the galaxies together. Zwicky reasoned that there must be more matter hidden somewhere in the galaxies, providing additional gravity. According to him, this missing massive amount must be hiding in huge clouds of hydrogen and helium, not yet formed into any stars. But no matter how hard he tried, he could not find these clouds. After 40 years in technology had become sophisticated enough, astronomers measured not only the speed of galaxies moving in space, but also their rotation speed. They could even break down the galaxy's rotation into angular parts, and calculate how the orbital speed of stars at different distances from the galactic center changes. Astronomers hope to observe stars at the edge of the galaxy rotating slower than stars near the center. This is the orbital model of planets in the solar system discovered by Johannes Kepler. It is a direct consequence of the fact that gravity weakens with distance, but it turned out that this is not the correct model for most galaxies. Instead, regardless of how far stars are from the galactic center, they all orbit at roughly the same speed. When this was discovered in the 1970s, it posed a challenge for astronomers. Test galaxy clusters because the outer stars are moving too fast for the galaxy. Since we do not observe galaxies spontaneously dispersing, the only solution seemed to be that there must be more matter hidden somewhere, inside or around the galaxies. For stars to move at the same speed, this matter would have to increase with distance to compensate for the predicted decrease in gravity. This requires a sphere of matter called a halo surrounding each galaxy. But while it was hard to ignore the clear circumstantial evidence for this new matter, searches yielded no minimal results. This situation threatened to push cosmology into crisis, until particle physics gave scientists a way out. In the process of trying to understand and unify the fundamental forces of nature, theoretical physicists consider the necessity of new energy-carrying particles. Theoretical predictions of particles have been correct in the past. For example, both antiparticles and neutrinos were predicted to exist before they were observed. Antimatter emerged from calculations George Paul Dirac performed in 1928 and was observed 4 years later. Neutrinos were invented by particle physicist Wolfgang Pauli in 1930 to explain the energy deficit in some reactions involving the weak nuclear force. He called his invention a desperate remedy, but explained that either a new particle had to be created or accept that energy could disappear from the universe. It took experimenters 26 years to perform an experiment detecting neutrinos. Following these successful predictions, particle physicists began talking about entirely new particles in an effort to unify the fundamental forces. These particles are so unlike normal matter that if they exist, they would create gravity, but otherwise hardly interact with normal matter. Astronomers immediately grasped this theory and realized that theoretical particles might be just what they needed to provide the missing mass. Indeed, when calculated, they found that the new matter could be 10 to 100 times heavier than normal matter, making them perfect for providing extra gravity to hold galaxies together. The difficulty was in finding these particles. They are predicted to interact very weakly with ordinary particles, to the point that they could exist as huge invisible clouds of particles around each galaxy. Astronomers coined the term dark matter to describe this type of matter and gradually incorporated it into every cosmological theory requiring additional mass. At the same time, physicists tried to deduce the exact nature of this dark matter. They proposed countless possibilities, and currently it is thought that the number of dark matter particles is as vast as normal matter particles. One of the first candidates was the axion, proposed in 1977 to adjust the behavior of the strong force and allow matter to be created at a slightly higher rate than antimatter. Researchers named this particle after a laundry detergent because they wanted to use it to clean up the mess between matter and antimatter. In 2005, experimenters thought they had found the axion, but subsequent studies refuted this conclusion. So the search continued. In the 1970s, particle physicists proposed the concept of supersymmetry. Known fundamental particles can be divided into two groups, fermions and bosons. Fermions are typically associated with matter because they cannot occupy the same physical space, and this resistance forms matter as we know it. Quarks, electrons, and neutrinos are all fermions. Quarks combine to form atomic nuclei with electrons orbiting around them. Meanwhile, bosons are related to force or energy. They can cluster arbitrarily close together, even occupying the same physical space. Representatives of bosons include photons carrying electromagnetic energy, W and Z particles carrying the weak nuclear force, and the famous Higgs boson thought to provide mass to particles. Supersymmetry theory suggests that every particle has a superpartner. Thus, the number of particles in nature is doubled. Each fermion is linked to a boson and each boson to a fermion. Candidates for dark matter are the superpartners of bosons, called photons, and thus form matter with mass. These supersymmetric photons are collectively referred to as neutralinos. The Large Hadron Collider in Switzerland can produce large quantities of neutralinos by colliding particle beams. But the machine's equipment cannot detect them. This is because neutralinos interact so weakly. Like ghosts passing through the walls of detectors the size of cathedrals without leaving a trace. However, this does not mean we cannot infer. The more energy neutralinos carry away, the greater the total energy deficit. When summing the energy of all detected particles and comparing it to the energy supplied for the collision, any discrepancy indicates that supersymmetric particles are being produced but immediately escape the experiment. If any energy deficit is observed, determining which type of neutralino among many is involved in this process could take a long time. Astronomers cannot assist because their computer models study clouds and dark matter, not individual particles. The smallest cloud they typically study has a mass greater than the Sun, and cannot extract properties of individual particles from such large-scale simulations. Capturing an image of a neutralino is the only way to learn about them. But that is also nearly impossible. Although dark matter is thought to interact very weakly with ordinary matter, conversely, it exists in extremely large quantity. At some point, a lot of dark matter will pass through detectors. To the extent that at least one particle could be detected. Currently, about half a dozen dark matter experiments are being conducted worldwide. Each system is designed to be sensitive enough to detect a dark matter particle if it exists. Some devices detect the heat generated when a single dark matter particle collides with a device. Others search for faint light produced when a dark matter particle hits an atom inside the detector. If any dark matter detector succeeds, physicists will measure the properties of the detected particle. But with the expected rate, at most only a few detections per year, it will take a long time to compile reliable results and conclude whether more than one type of dark matter exists. If neutralinos are detected, they would undoubtedly be the dark matter scientists are seeking. They may not exist in sufficient quantities or be stable enough to last long and provide the necessary gravitational force. When testing the diversity and stability of dark matter, astronomers must collaborate. Because supersymmetric particles interact very weakly with ordinary matter, it does not mean they do not interact with each other. According to dark matter models, a pair of identical particles will annihilate upon collision, releasing a pair of gamma rays. Astronomers hope that such annihilation signals could come from the center of our galaxy, where dark matter is expected to be dense, or from nearby dwarf galaxies. They have used satellites to search for these signals. Once astronomers determine the relative proportions of axions, neutralinos, and any other dark matter types, they will have to consider neutrinos. Because recent laboratory experiments have shown that these weakly interacting particles, once thought to be massless, actually have a small mass. Therefore, they will contribute to gravity wherever they're found. Many astronomers increasingly believe in the existence of dark matter, while others grow more skeptical. This is because dark matter theory has a fatal flaw in the form of an implicit assumption. Its existence depends on the accuracy and applicability of Newton's law of gravity in very weak gravitational fields. Scientists already know that Newton's law of gravity fails in strong gravitational environments, where it must be replaced by Einstein's theory of general relativity. Perhaps the same is true at the other end of the scale, where gravity is particularly weak. In 1981, when others began accepting dark matter, Israeli physicist Mordechai Milgram proposed a modification to Newton's law of gravity to explain galaxy rotation without new particles. Remember, gravity causes objects to accelerate. Milgram's proposal was that Newtonian gravity changes when below a certain acceleration value. Therefore, instead of the force decreasing by the inverse square law, meaning when distance doubles, acceleration reduces to 1/4, it starts decreasing more slowly. Only by the simple inverse law, meaning when distance doubles, acceleration reduces to half. The critical acceleration when this occurs is very small, no greater than the acceleration caused by the gravitational field of it, but it has significant effects in the outer regions of galaxies. Milgram showed that by making weak gravitational fields slightly stronger than expected, the theoretical model could successfully explain stars moving at uniform speeds to the galaxy's edge. In most cases, this shows better agreement with observations than dark matter models. He called his idea modified Newtonian dynamics, abbreviated as MOND. Although this view is still supported by only a minority, if experiments searching for dark matter yield no results, and the Large Hadron Collider doesn't produce neutrinos, then perhaps astronomers will have to reconsider what previously seemed impossible. Newton's theory of gravity needs updating. The limitation some see in MOND is that it lacks a theoretical foundation. This makes many astronomers reluctant to accept it. But there are precedents in history of discovery first, explanation later. Kepler proposed the laws of planetary motion in the early 17th century, without a theoretical foundation. He simply analyzed data and found equations describing them. Only in 1687 did Newton's theory of universal gravitation help us understand why Kepler's laws were successful. Throughout astronomical history, many laws were inferred from observations before having explanatory theory. However, MOND is not perfect. This theory attempts to describe the motion of galaxy clusters, requiring more matter than observed to explain. So we still need dark matter to explain this. Perhaps not, because astronomers believe there exists a significant amount of ordinary matter hidden in galaxy clusters as hot gas. If they can detect this with ultraviolet telescopes, thought to be emitted from there, MOND's problems with galaxy clusters would be solved. In the journey to prove the existence of dark matter, astronomers recently used a technique called weak gravitational lensing. This idea comes from the concept of curved space in general relativity. They searched for a nearby galaxy cluster, which can create significant curvature in space structure, then observe light from more distant objects passing through the cluster. When light passes through this galaxy cluster, it is deflected due to the curvature of space, and this distorts the images of distant objects, like a giant cosmic funhouse mirror. By analyzing these distortions, astronomers hope to measure the curvature of space around the galaxy cluster. If the curvature is greater than could be explained by the distribution of galaxies, the solution is to invoke dark matter and use the curvature to build a dark matter map. However, there is another interpretation that suggests the greater curvature indicates the MOND correction is at work, producing a larger than expected. There is a particular battlefield for competing theories, called the bullet cluster, where two galaxy clusters are colliding. Observations show that the gas between galaxies has diminished, but weak gravitational lensing indicates strong curvature still exists around the galaxies. This could be the massive dark matter region needed to hold the two galaxy clusters together. Or it could also be areas where bond needs to be applied. Other galaxy cluster collisions show similar activity, and therefore they don't help astronomers distinguish between dark matter and bond theory. But recently, they found something that might help break the deadlock. An object that puzzles everyone. The strangest galaxy cluster collision, Eagle 520. In this particular cosmic explosion, observational results from gravitational seem to show that dark matter has separated from the galaxies. This completely contradicts the predictions of established dark matter, and the only way to explain dark matter reacting this way is to hypothesize that dark matter is interacting with itself, creating a force that only acts on dark matter. Such a hypothesis would also solve the problem with the bullet cluster collision. Computer models cannot explain the collision speed between clusters, but an unidentified dark matter force could explain everything. The current picture is more fragmented than ever. MOND does not apply in all situations. It requires about twice the amount of matter we see in the universe. And dark matter needs a new kind of force. You need to unify information about it. Therefore, the key point is that no one knows what dark matter is, or even if it exists. It could be an illusion due to our misunderstandings about gravity. In the near future, major research facilities will conduct new experiments. The Large Hadron Collider, dark matter detection devices and satellites are ready to receive signals from dark matter, promising to reveal information or permanently disprove the existence of dark matter.